Hello everyone, I'm Anuj. Let's start with second part of our project, that is implementation of FIR as a hardware accelerator on FPGA. Let's go to Quartus. Again, we'll be proceeding with the creation of new project. We'll go to the directory. This demo hardware. We'll give the project as, let's name it hardware FIR, and I'll name the top level design entity as Qsys. I'm using this name because I'll generate my system in Qsys and I'll use the same system in Quartus. So the top level design in Qsys will be my top level design in Quartus. So that's why I'm giving the same name. We'll discuss on it more later. I'll be using D1 board, which has Cyclone 2 with 484 pins. And if required, we'll use the model sim for simulation. The project is created. Now let's go to Qsys. Qsys is a system building software. Here you can build your whole system by just connecting different components. You can just drag and drop different components, create your own custom components. So in this case, we'll require 128 type FIR filter as a custom component. We'll be creating a new component for that. So let's start with creating the new component. We'll name the component as FIR 128, and let's use the same name to display. And as you can see here on the left hand side, there are different groups and different components are included in different groups. So we can assign a custom group also. Let's call it my component. After that, we need to define the Verilog file behind this component that will describe the hardware. So we'll include the Verilog files, the hardware accelerator file, flip-flop file, accumulator file, and multiplier file. These four files describe my new component, that is FIR. So the hardware accelerator file is the top level file, and all the three files are the mega wizard function files, which are instantiated in this top level file. This is the multiplier, this is the flip-flop, and this is the accumulator, which constitutes my FIR filter. I will analyze the system for any errors or warnings. I'm good to go. This parameter is defined inside my hardware accelerator file. This is parameterized, so I can edit it anytime when I import this component in any of the system. These signals are the top level signals being defined in my top design module in my port list. There is a certain protocol to be followed for the naming these signals. As you can see, I followed some protocol because I want these signals to be part of a Avalon memory map protocol. If you don't follow the convention, you need to manually assign each signal to some different protocol if you want, or just an arbitrary signal. So this is the protocol for Avalon memory map slave. So these are the total interfaces available on my custom component. This is the reset pin, and we need to synchronize it with the clock. This is the clock pin, and this is the Avalon memory map slave interface, and we need to give the reset signal to it. So we are done with the custom component design. We can finish this to successfully create the custom component. And you can see here there is one group created called my component, and there is the FIR 128, our custom created component. So now let's start with importing different components in our system. So we'll be importing first NIOS 2, This is the configuration window for NIOS 2 and we'll be using the economical version of this core. Let's import on-chip memory, and to be on safer side we'll use 8192 bytes of on-chip memory. We use JTAG UART for communication with the system, between the system and the PC. We need performance counter to evaluate the performance of a custom created FIR component. And apart from this, we need FIR 128 filter that we just designed. So you can see here the operand size which we can see in the parameter window in this custom component is parameterizable whenever you will import this component in any design. Now let's supply the clock and reset to every module, every component. Let's give clock to NIOS 2, to on-chip memory, to JTAG, to performance counter, and to FIR. Let's give the reset to on-chip memory, NIOS, performance counter, JTAG, and FIR. Now we have two ports on the NIOS 2 processor. One is the data master and another is instruction master. Instruction master is always given to the memory from where the instructions are fetched, and data master is given to all of the blocks for the data communication. Let's assign the interrupt pins. You guys can see there are a lot of errors downside. This is because we have not assigned base address to any of the component. So let's assign base address. So we are left with two errors, and these are because we have not assigned the interrupt and reset vector of the NIOS 2 processor. So we need to assign the reset vector to the on-chip memory and the exception vector also to the on-chip memory. These options are visible only after you connect all the system. So we have created our system in Qsys. Let's save the system. We'll name as Proj Qsys hardware FIR. If you guys remember, we gave the same name to the top level design entity while creating the project in Quartus, because the top model will be the same in both the Qsys and the Quartus. So this top design entity has to be same. And let's generate the system to get the Verilog files behind our system. After getting the Verilog files, we need to import those Verilog files in our Quartus project, and there is also one .qip file being generated by Qsys. So you have option, you can either import the .qip file alone into your Quartus project, or you can import all the Verilog files for whole system into your Quartus project. So we'll be proceeding with importing just one single file, that is .qip file, in our Quartus project. So this Qsys generation is completed successfully. Let's come to Quartus. Let's import the .qip file as discussed. So this is the folder created by Qsys. You can see this is the top level Verilog file being generated by Qsys, and these are all the submodules. So if you want to import all the Verilog files, you need to import all these files and also this one into your Quartus project, or otherwise you can import just one single file, that is QIP file. It is this one. So we'll import the QIP file. So here you can see QIP is imported. Now we need to go to assignment editor to assign the pin for the clock. We are assigning the pin for only clock because all our components are built into the FPGA. None of them will be using the IO pins of the FPGA, so we don't need to assign this pin to anything like NIOS 2, on-chip, JTAG, performance counter, FIR, all are built into the FPGA without using the FPGA IO pins. The assigned location and IO standard for clock. For this particular D1 board, the location of the clock is pin L1, and we use a 3.3 volt LVTTL standard for the IO standard. Let's save our assignment editor, and we are good to compile our Quartus project. Takes a bit longer. By the time we can create a project in NIOS 2. So this is the work directory given to the Quartus project also. So you'll give the same work directory to NIOS. So you can delete all the previous files or folders being included in the NIOS. The next step we'll be doing is we'll be importing the system file on our D1 board. This Quartus compilation at the end will give us a .sof file which will represent the whole system, and that SOF file needs to be burned into your D1 board using the programmer. And you also get a .sopc info file that needs to be imported into the NIOS 2 SBT for Eclipse to support the software. And after burning the .sof file into the D1 board, while opening NIOS 2, we'll import the .sopc info file into the NIOS 2 to support the software programming, and there we'll be writing a C code to be burnt into our NIOS 2 processor. So we have successfully compiled our Quartus design. As discussed, we will get a .sof file. So this is the .sof file created by Quartus. We will be exporting this file to the board. Let's go to programmer. First, let's switch on the board. So the board is on. So right now we cannot see any hardware connected. We need to restart the board once. Now you can see the USB blaster cable. We'll import our .sof file. And we'll burn it into the board. We have successfully done that. Let's save the CDF file. Now the system is built into the FPGA chip. So the system includes the NIOS 2 processor, the on-chip memory, JTAG UART, performance counter, and FIR. And now to work the system successfully, we need to program the NIOS 2 processor for this specific functionality. For our project, the NIOS 2 processor will be giving inputs to the FIR and will read back the final answer of the FIR. So let's start with creating a project in NIOS 2. As discussed, we'll import the .sopc info file. We'll name the project as project NIOS hardware FIR. We'll check the directory. This directory should be the same. This should be included in the same workspace. And here's the template. So there's one hello world template and there is one hello world small template. So as we are using the on-chip memory which has a limited size, for that we'll be using the hello world small template because it loads limited library which occupies less space in the board. So NIOS 2 project is created. So you can, this is your project folder and this is the .c main file that you got from NIOS 2, and it should have a hello world template to print hello world from NIOS 2. So this is your main C code, and you can try building this code. Let's build project. So the project is successfully built. Now to check the proper connection between your system and the PC, you can just try running this project as run as NIOS 2 hardware. So it will run this code on the FPGA board, which already contains this NIOS 2 processor and other peripherals. While doing the first time, you all will face this window. So in this, you need to go to target connection, you need to refresh the connection to see the communication cable that is USB blaster. Apply it. For now, just ignore the mismatch system, timestamp and system ID, as we didn't include these components in our Qsys. Let's run it. So you all guys can see we got the hello from NIOS 2 on the NIOS 2 console. So this is being sent by the NIOS 2 processor on FPGA board. Now our task is to program the NIOS 2 to send the input values to the already implemented hardware FIR and to read back the final answer, and also to evaluate the performance. So for that I have a C code. We'll just copy that C code here. So here you guys can see, and the one thing is, in Qsys you can see the base address being allocated to different components. So the base address allocated to performance counter is 5200 and to FIR is 5000. So let's give the same address in our C code. For FIR it is 5000 and for performance counter it is 5200. It's good. So here are the input values and coefficients for FIR, and this three line represents the start of the performance counter. And now I am sending one by one the value and coefficients. This X is the input value, Y is the coefficient. So I am sending value, coefficient, value, coefficient, value, coefficient, value, coefficient serially on the same data path of the Avalon memory mapped slave interface. Finally, I am reading back the value, I am printing the value, and I am stopping my performance counter, and I am displaying the number of cycles being consumed by the performance counter. So this code is all good to go. Let's run this code as NIOS 2 hardware, which is the final step of our project. You guys can see the processing percentage on the right side. This is the 9% completed till now. Okay, so we are successfully done with our project. The output of the FIR filter is minus 34 and the number of cycles consumed during this FIR calculation is 19402, that is 19,402. So as you guys can see, we have displayed same thing here in our code, and we got the same thing at the NIOS to console. This console represents the data being sent by the NIOS to processor, which is on the FPGA board. I have some guidelines to be followed during this project. Please follow these guidelines to be on safer side. I hope these guidelines will protect you from some of the errors that you'll be facing during the project. Thank you guys.